Hmm. My pen again. Oh, there it goes. Okay, I think I'm gonna have to use that other app again. Let's see. Is it going? Okay, let's try and use this, and then if it doesn't work, we'll switch. Okay, so so some more localization.
Taylor, I have a question, not so much about any particular mathematics today.
Yeah.
But maybe sometime this week or sometime in the relative near future, maybe this is something we can do in office hours too. Could we talk a little bit more about like the motivation for these things, like motivating these concepts from like because I feel like maybe that's a little hard.
Yeah, I mean, so the one of the big reasons to do this is for algebraic geometry and for scheme theory. So a lot of these things that we do are related to geometric concepts, as you've seen.
Yeah.
So you'll see that this particular one is about a lot of it's about like gluing things together to make global objects. Yeah, but yeah, we can talk more about this in office hours.
Cool. Yeah, I'll come with like a better like. All right, we've talked about these things, and this is how I think it goes. And then we can like
Yeah, I mean, we'll see some applications already. We'll see. I mean, we're gonna get to applications pretty soon. Like one of the things that you can do is like you can check that a module is zero, if and only if it's zero at all its localizations at prime ideals. Or you can check that a map is injective if and only if it's injective at all the prime after localizing.
okay.
Things like that. So a lot of it is like you reduce a lot of problems to local problems in algebra. That's another thing.
Okay. Cool. Yeah, 'cause it's like for me, it's like I gotta like tell myself some kind of story to like actually ingrain all this stuff in my head. Otherwise, it's like
Yeah.
disjoint.
Yeah. The pictures are good for that.
Yeah. No, I mean absolutely. I just like I'm trying to like develop like a cohesive understanding, I guess.
Yeah.
But yeah.
And that's great. Yeah. So let me start with the theorem that we've discussed already. So if we have S a subset of R, a multiplicatively closed set, then here, spec of R of S, which is just the same thing as spec of inverse of R, can be identified with here the set of P in spec of R, such that P intersect S is empty. Okay. All right. So furthermore, its topology has the subspace topology. Okay, so we need some stuff to prove this. So we need this, but there's an easy direction. Okay, so okay, so first we have a morphism. So okay, so we have a morphism of rings. The localization map from R to R of S. Again, this is the same thing as S inverse of R. And we want to show that these two things are the same. The inverse image of prime ideals and the set of prime ideals in Spec of R such that P intersect S is empty. Okay, so this is what we want to show. Okay, so now I'm going to show the easy direction, which is this containment. Right? And so we're going to let Q be an element of spec R of S. So we claim that LS inverse of Q intersect S is empty. I mean, this is easy to see. So if not, then there exists an S, an element of S intersect Q, which implies that 1 is an element of Q, because we can invert it, right? So since this is an ideal in the localization, S is invertible, right? And this implies that Q is equal to R of S, but the whole ideal, with the whole ring, sorry, is excluded as a prime ideal in this spec of R of S by definition. By definition. Okay. We'll come back to the other way. All right. So, okay, so we'll come back to the other direction. Okay. So, all right. So the next thing I want to do is I want to show how localization in exact sequences behave. Okay. So, so note that so if M and N, this is kind of a setup, are R modules with okay, so let's do, I just have to set up a bunch of things. So there we have some R modules. We have S, a subset of R, a multiplicatively closed set. And F from M to N is a morphism of R modules, R module homomorphism. Then we get a new map here. So then we get a map here, Fs. Okay, so that's a big S from S inverse of M to S inverse of N. And the idea is that it behaves exactly like you'd expect it to, Fs of M over S. So this is F of M over S. So it behaves linearly, okay? So this gives us a functor from morphisms from morphisms of modules to the localized version. So So what do I want to say about this is that, so note that this map f of s can be considered as a as a map of R modules S inverse of R modules or abelian groups. Okay, I guess the most structure it would have is as an S inverse of R module, but and exactness in each of these is all the same. Let's say not exactness. Let's say injectivity or surjectivity. In each of these is the same. So like a morphism of R modules is injective if and only if it's injective as a morphism of abelian groups. And it's surjective if and only if it's surjective as a morphism of abelian groups. That's because, you know, something goes to zero if and only if f of, you know, if f of the so something goes to zero if and only if the f of the thing is zero, and that happens no matter what you know, what category you're looking in, right? And it's surjective if and only if it if and only if it's surjective in any one of these categories. You know, for everything in the domain, there's something in for everything in the codomain, there's something in the domain that maps to it. It's not necessarily true that all maps of R modules, S inverse of R modules and abelian groups are the same, but just that you can check their properties on the level of abelian groups. You can check injectivity and surjectivity on the level of abelian groups. Okay, so the fact that they're morphisms of R modules says that they're linear. Okay, so now let me state the thing that I wanted to say. So here's an important lemma. Oh, what the heck? There we go. Here's an important lemma. Okay. So let 0 to m prime to m prime prime. Okay, we'll do this one as p and this one as j. So be an exact sequence of R modules. Then when we localize, we get an exact sequence. 0 to S inverse of m prime. Okay, so now this is JS, S inverse of m. This is PS, S inverse of m prime prime. So 0 is also an exact sequence of R modules. Okay, so let's do the proof of this. And in the proof, I'm going to remind you what the definition of what it means to be an exact sequence. Okay, so proof. So what do we need to do? So we need to check. To check three things. So first, that P of S is surjective. That J of S is injective. And that the kernel of P of S is equal to the image of J of S. Okay, so this is what this is pretty cool. Okay, so let's do this. Do this. Okay, so let's check surjectivity. PS. Okay, this is the definition of what it means to be exact. Okay, so what do we need to show? We need to show for everything in here in the codomain, there exists something in the domain mapping to it. Okay, so if m prime prime over s prime prime, this is an S inverse of m prime prime, right? Then, well, there exists some m in M with P of M is equal to M prime prime by surjectivity of P. Okay, and then this is easy. So then we have, so this gives P of S of M prime prime over S prime prime. And so this was P of M prime prime over S prime prime. And so this is M over S. Oh, sorry, I did that wrong. This should be M here. This is M prime prime over S. Okay. So now we need to do a little bit of injectivity. So let's do the injectivity. So this is the easiest part. Injectivity of JS.
How come the S lost its prime prime?
Oh, yeah, it did lose its prime prime. There you go. All right, so there we go. Okay. Okay. So injectivity of this. So what we need to show is the again. So a map of modules f from M to N is injective if f of M is equal to 0 implies M is equal to 0. Okay, so the kernel needs to be the 0 module. Okay, and that's what we're going to check. So if JS of M prime over S prime is equal to 0, right, then JS M prime over S prime is equal to 0, because that's the definition of the map. Which means there exists some S and S with, well, SJS of M prime is equal to 0. Okay. So this thing, so what does this mean? So this implies, that, okay, so I'm going to just omit the quantifier here, but we can pull this inside. J of S of M prime is equal to 0. Okay. And this implies, so this thing here is J of S of M prime is equal to 0. And this implies that M prime is equal to 0 in S inverse of M prime. Right? Because I'm using the property of the characterization of the kernel. This implies that S of M prime is equal to 0 in this. So Oh, and then we have that. So this implies that. Sorry, this is in M. Okay, and so we have that M prime over S prime. Well, this is SM prime over SS prime, and then this is 0 in S inverse M, which proves injectivity. Okay, so you can cancel like this, and so you can check that that's satisfied. Okay. Okay, so now we need to prove exactness. Okay, so we're showing that the image of J of S is equal to the kernel of P of S. Okay, so suppose something is in the kernel. We need to show it's in the image. P of M over S is equal to 0 for M over S in S inverse of M. Okay, so as we just saw, right, this implies there exists some T in S such that T of P of M is equal to 0. So we had an argument just like this here. So the same idea is here. Okay. Well, this implies that P of T of M is equal to 0, right? Which implies that, well, T of M is in the kernel of P. And by exactness, this is equal to the image of J. This is by exactness of the original sequence. Okay, so this implies that there exists some M prime, and M prime, such that Tm is J of M prime. Okay, and now we got to put everything together. Okay, so we have Js of M prime over St, right? Okay, so again, what are we showing? We're showing that here. So the whole goal of this is to show. So let me just. The goal is to show that M over S is in the image of J of S. So that the image of J of S is the kernel. Okay, and now we're getting to that part, and I claim that this is the element that does it. So this is J of S M prime over St. So this is Tm over St. And you can cancel elements like that, and this is Ms. Okay, and so we proved that it's in the image, so we're done. Okay. So this is a really cool theorem. Yeah. So what did we just prove? So we just proved that if you have an exact sequence and you localize it, it remains exact. Okay. So the injection, in particular, so what does this show in particular that localizations of surjections are? So note that this implies localizations of surjections are surjections. Localizations of injections are injections. Okay. Okay. So this is cool. What are some other consequences? So more consequences. Let's do. I don't know. We can do another color. More consequences. Okay. So one, if M prime is a submodule of M, then S inverse of M prime is a submodule of S inverse of M. Another one is that if M prime is a submodule of M, then the localization of the quotient is isomorphic to the quotient of the localizations. Okay. So the proof of this is easy. Okay, so this is how you should be reading exact sequences. So we'll have an exact sequence, 0, M prime, M, and then we have M mod M prime. Whenever you have an exact sequence, the co-kernel or the right-hand term is always going to be isomorphic to a quotient like this. So you take S inverse of this, and you get, 0, S inverse of M prime, S inverse of M, S inverse of M over M prime, right? So, and then because the sequence is exact, right? This map is surjective with kernel this thing. And so this is like the first isomorphism theorem. Okay. Okay, so what other consequences do we have? A third consequence is that, if M1 and M2 are submodules of M, then, if we add two things together, they behave well like this. So the localization of the sum is the sum of the localizations. And, we can do the same thing here with intersections. Okay, so like localizations, super nice. It behaves super, super well. Okay. Okay. So the other part that we wanted to do.
Can I ask you a question quick?
Yeah.
So we're seeing here that localizations behave really, really well. Are there places where localizations don't behave
No.
well.
No,
So
no.
they,
It depends on what you mean. Like, so this is just saying that, like, I don't know, it does what you want it to.
yeah, I mean that's what I'm getting at. It's like, all right, it does all the stuff that we would want this making fractions to work.
Yeah, it's nice.
Great, cool. All right, so
I mean,
I was just
yeah, for the most part, that's what you should think, is that it behaves super well.
okay, cool.
Yeah. Okay. So there is a universal property of localizations. Okay, so let's just do the universal property. Okay. Okay, so let S be a subset of A, be a multiplicatively closed subset. Okay, so if F from A to B is a ring homomorphism. Okay, so the idea is that, like, if this multiplicatively closed set gets inverted under some ring homomorphism, it's going to factor through the localization map. Okay, if this is a ring homomorphism such that such that for all S in S, f of S is invertible, is a unit, then F factors through the localization. Okay, what does this mean? I.e., there exists some F S. Let's see, that's kind of a bad name. Okay, I'm just going to use it anyway. This is not the image of this map under localization, such that, well, I guess it is kind of, because if you localize things that are already invertible, you'd really do nothing. So, like, if I take a field and I localize it, invertible elements, the localization of a field is a field. It's the same thing. Okay, so there exists a unique, map. Okay, let's write this correctly. Here from S inverse of A to B, such that the following diagram works. You have A, and this goes into S inverse of A. This is our original map, F here. And then I'm saying that this thing fits into this diagram. So this is the localization map. Okay, and so yeah, so it's like if S becomes invertible, then you get this factorization. Okay, so so we'll do part of this. Okay, let's do part of this theorem. Okay, so part of the proof. Okay, so I'm going to show you that this map F of S exists. Okay, so we can get a formula for F of S immediately, right away. Okay, so here we have that. Excuse me. Okay, so if A is in A and S is in S, right? So we have that F of A. Well, this is F of S of AS over S. And if this is a ring homomorphism, this needs to be F of S of AS F of S S. Okay? And now this thing needs to agree with F. So this is F of S AS. This is F of S. And then by hypothesis, this was invertible, right? So this thing was invertible by hypothesis. Okay, so this tells us that this map here is equal to F of A, F of S inverse. Okay, so this proves that the map is unique. Exists and is unique. Okay, but okay, so there's some things to check. So it remains to check. Right, two things, right? Well, that it's a homomorphism. I guess by exists, let me just say the map is unique. Let's just say it doesn't exist. The map is unique, but we need to show that it's a homomorphism, that it is a homomorphism. And two, that it is well defined. Okay, well definedness is means that these things here are these things here are really equivalence classes. And we need to check that the map doesn't depend on the choice of equivalence class. Okay, i.e. if A1 over S1 is equal to A2 over S2, now I'll remind you that this means that then this implies that that f of A1, fs of A1 over S1 is equal to fs of A2 over S2. This is what you need to check. Okay, so this I'm going to leave as an exercise for you guys to do. I think it's a good exercise. And then, so I just want to remind you again what this means, right? So this means if and only if there exists some S in S such that S times what we would S2A1 minus S1A2 is equal to 0. Okay, so that's what we're looking to do. Okay, so if these two things are something satisfying this, you need to show that these two things are the same. And I guess the trick is to, like, I guess we're pretty close to it, but yeah. Anyway, you have to use this map. Okay. Let me give you a slight strengthening of the universal property. Okay, so there's the stronger part of the universal property is that you have this thing, right? But there's something even stronger that you can say, and it says that okay, so given if G from A to B has the following properties. Well, one, that S is an element of S implies G of S is a unit. Two, G of A is equal to 0 implies that SA is equal to 0 for some S and S. And three, that every element of B of B is of the form GA GS inverse, then B is isomorphic to S inverse of A. Okay, so note that we have so I guess here's the proof. So so by the universal property, and 1, there exists a map okay, so we have this factorization. A goes to B. This goes to S inverse of A. This is the localization map. And then there's this G of S map here that fits into the diagram. So this diagram, of course, is commutative, right? This diagram is saying that G is equal to LS GS. Okay, that's why we call it factoring. Okay, because G factors like this. Okay, and then so 1 tells us this. 2, so I guess 3 tells us surjectivity. 3 tells us that the map G of S is surjective. And 2 is really telling us that the map is injective. Okay. Okay, and so you have a ring homomorphism that is injective and surjective, so that proves this is isomorphism. Okay. Okay. So so now I guess we can go. So now I guess there's kind of 2 ways that we can do this. Let's go back to the very beginning here. In the very beginning, we were showing this thing
Taylor?
here. Yeah.
What we just wrote in red,
Yeah.
are we just like, is that like, should we call that like the stronger version of the universal property?
You call it the characterization of the localization. So this thing here. So this is a theorem. So this is the characterization of S inverse of A. Right. So, and I guess maybe better than that, it's not just S. That's kind of an abusive notation, but characterization of the map LS from A to S inverse of A. Right. So if you have a map and it looks like a duck and it quacks like a duck, then it is a duck. It's that type of theorem. Okay. So, okay. So what I wanted to say is that there's kind of 2 ways to do this second part of the theorem. So now let's go back to here. The theorem at the very beginning, right? So the hard direction right was to show that this other containment here. right? And so we want to show that if P intersect S is empty, then S inverse of P is a prime ideal. Okay, so the idea was that if you take so let's do this. So we have 0 to R to, sorry, let's do this. 0 to P to R mod P. Sorry, to R mod P, like so. Okay, so then this gives you the exact sequence 0 S inverse of P, or S inverse of P, S inverse of R, S inverse of R mod P to 0. This is still exact. And so this thing is isomorphic to. So this is the localization of a domain. So it's still a domain. Okay, and so the localization of a domain is still a domain. Okay, and then this proves that this is a prime ideal of spec, or sorry, of S inverse of R. Okay, and so one thing is you could view this, so S inverse R mod P. This is the same thing as S bar inverse of R mod P, where S bar is the image of S in R mod P. Okay, so the point is that you could use this exact sequence, this localization, to deduce things about this exact sequence. So I'm going to end here, and then I'll be here for questions if you guys have some.